In the ancient world of the Cretaceous period, a terrifying predator roamed the vast landscapes of what is now South America. Stretching over 40 ft long and weighing as much as 8 tons, this creature was the very embodiment of prehistoric power and ferocity. It wasn't just a rival to the famous Tyrannosaurus rex, it was its worst nightmare, the Giganotosaurus. With razor-sharp teeth, a powerful skull designed to crush bones, and incredible speed, this apex predator struck fear into everything in its path. But what made Giganotosaurus such a horrifying force of nature? How did it grow to become one of the largest carnivorous dinosaurs to ever walk the earth? Join us as we unravel the secrets of this giant and its fight for survival in a world full of danger. Giganotosaurus was a massive meat-eating dinosaur that lived about 99.6 to 95 million years ago during the late Cretaceous period in what is now Argentina. This was a time long before humans walked the earth, when the planet looked very different. This incredible dinosaur was first uncovered in 1993 in the Cordilleras Formation, which is part of Patagonia in South America. What made this discovery so special was that the fossil they found was almost 70% complete, allowing scientists to get a rare and detailed look at this giant creature. In 1995, researchers officially named it Giganotosaurus carolini. The name Giganotosaurus means giant southern lizard, highlighting its enormous size and the fact that it lived in the southern part of the world. The second part of its name, Carolini, is a tribute to Reuben Carolini, the scientist who played a key role in the discovery. Before this major find, scientists had already discovered other remains like a tooth, a jawbone, and some footprints, which were later connected to Giganotosaurus. These additional pieces helped researchers build a more complete picture of this incredible predator. When scientists studied these fossils, Giganotosaurus quickly became the subject of intense debate. It was one of the largest meat-eating dinosaurs ever discovered, and paleontologists eagerly discussed just how large these terrifying creatures could grow. Its enormous size and powerful presence continued to fascinate scientists and dinosaur lovers around the world, keeping Giganotosaurus a popular topic of research and discussion. Giganotosaurus was one of the biggest meat-eating dinosaurs to ever roam the earth, but figuring out exactly how big it was has been tricky because only partial remains have been found. For the most complete specimen, scientists believe it could have been around 12 to 13 men long, with a skull that measured about 1.53 to 1.8 meters in length and weighed between 4.2 and 13.8 tons. There's also a piece of jawbone from a supposed larger individual, which some scientists think could have belonged to an even bigger Giganotosaurus, possibly reaching a length of 13.2 meters. While some researchers argue that Giganotosaurus may have been even larger than the famous Tyrannosaurus rex, others believe the two were about the same size. And the biggest size estimates for Giganotosaurus might be too exaggerated. This terrifying predator had a skull that was low and broad, with rough, bumpy nasal bones. In front of its eyes, there was a unique ridge-like crest on the bone that helped form the upper part of its face. The front of its jaw was flat and featured a downward-pointing chin at the tip. Its teeth were sharp and jagged, designed for slicing through flesh with a sideways compression that helped them cut deep. Giganotosaurus had a powerful neck to support its head, but its shoulders were relatively small compared to the rest of its massive body. Giganotosaurus, a member of the Carcharodontosauridae family, is one of the most well-understood dinosaurs of its kind. This family includes other giant theropods like the closely related Mapusaurus and Carcharodontosaurus. Giganotosaurus is believed to have been homeothermic, meaning it had a body temperature regulation system similar to warm-blooded animals, but not the same as mammals. Its metabolism was likely a mix between a mammal and a reptile, allowing it to grow quickly and stay active. With its powerful jaw muscles, Giganotosaurus could snap its mouth shut rapidly, using forceful bites to capture and bring down prey. Its chin might have played a role in supporting its jaw, especially when delivering such a strong bite. As the dominant predator in its environment, Giganotosaurus likely hunted large prey, such as young sauropod dinosaurs, making it the top hunter in its ecosystem. In 1993, Ruben Dario Carolini, an Argentine fossil enthusiast, made a jaw-dropping discovery while cruising through the harsh, sandy badlands near Villa El Chocón, a small town in Patagonia's Neuquén province. Carolini was driving a dune buggy across the rugged terrain when he noticed something unusual sticking out of the ground. Upon closer inspection, he realized it was no ordinary rock. It was a massive, fossilized leg bone. Experts later identified it as the tibia of a gigantic theropod dinosaur, one of the meat-eating giants that once ruled the Earth. Understanding the significance of his find, Carolini quickly reached out to paleontologists at the National University of Comayagua. They wasted no time assembling a team to investigate the site, and what they found was beyond anyone's wild expectations. Word of the discovery spread like wildfire, and in 1994, two leading paleontologists, Rodolfo Correa and Leonardo Salgado, shared the groundbreaking news at a high-profile Society of Vertebrate Paleontology meeting. Among the audience was science writer Don Lessem, who was so captivated by a photograph of the enormous leg bone that he decided to fund the excavation himself. As the team carefully dug into the fossil-rich soil, they unearthed a treasure trove of dinosaur remains scattered over an area about the size of a small room, 10 square meters. Piece by piece, the skeleton of this ancient predator came to light. Amazingly, they uncovered around 70% of the dinosaur skeleton, including parts of its skull, backbone, hips, shoulders, and hind legs. It was one of the most complete finds of such a massive predator ever recorded. By 1995, after extensive study, Correa and Salgado gave this colossal dinosaur a name that suited its grandeur, Giganotosaurus carolini. The name combines Greek words meaning giant southern lizard, and the species name honors its discoverer, Ruben Carolini. Although parts of the fossil were still encased in plaster at the time, it became the official reference specimen, or holotype, for this newly identified species. Today, the remarkable discovery takes center stage at the Ernesto Bachmann Paleontological Museum in Villa El Chocón, which opened in 1995, thanks in part to Carolini's dedication. Visitors can see the actual fossils displayed on a sandy floor, giving a sense of how they were found. Nearby, tools used during the excavation provide a fascinating glimpse into the careful process of uncovering ancient history. In the next room, a life-sized reconstruction of the Giganotosaurus skeleton looms over visitors, capturing the awe-inspiring scale of one of the largest and deadliest predators ever to roam the Earth. One of the most exciting things about theropod dinosaurs is that they were home to some of the largest and most fearsome predators ever to walk the Earth. These mighty creatures, which ruled the land during the Mesozoic era, have fascinated scientists and the public for almost 200 years. The story begins in 1824 with the discovery and naming of Megalosaurus, one of the first dinosaurs ever identified. Its enormous size immediately captured attention and sparked a wave of curiosity about these prehistoric giants. Fast forward to 1905, when the famous Tyrannosaurus rex was introduced to the world. T-Rex became a symbol of prehistoric power and held the title of the largest theropod for nearly 90 years. But as the decades rolled on, other massive theropods began to emerge, challenging the reign of T-Rex and fueling debates among scientists about which dinosaur deserved to be called the ultimate predator. The debate took an exciting turn in the 1990s with groundbreaking discoveries in Africa and South America. Among these was the discovery of Giganotosaurus, a dinosaur that could potentially outmatch T-Rex in size. Paleontologists Rodolfo Coria and Leonardo Salgado, who first described Giganotosaurus, identified it as the largest theropod ever found in the southern hemisphere, and possibly the world. Although Giganotosaurus's fossil record was incomplete, clues from its bones painted a picture of a colossal predator. For example, its thigh bone, or femur, measured a staggering 1.43 longer than that of Sue, the most complete T-Rex specimen ever found. The femur's thickness and the overall robustness of Giganotosaurus's bones suggested it was not only longer, but possibly heavier than its North American rival. Giganotosaurus's skull alone was estimated to be about 1.53 meters long, roughly the height of an average adult human, and its body stretched an incredible 12.5 meters from snout to tail, weighing between 6 and 8 tons. This giant predator would have been a terrifying sight as it hunted across the plains of prehistoric South America. Its immense size and power showcased the incredible diversity and adaptability of theropod dinosaurs. These discoveries reignited the long-standing debate over which predator was truly the king of the dinosaurs. Was it the legendary T-Rex with its crushing bite and iconic fame, or the lesser-known but equally impressive Giganotosaurus? Beyond the debate, these findings open new doors to understanding the world of the ancient giants. Each discovery is like adding a piece to an immense, thrilling puzzle, one that continues to captivate our imagination. In 1996, paleontologist Paul Sereno and his team made an incredible find in Morocco, a nearly complete skull of a fearsome dinosaur known as Carcharodontosaurus. This discovery was thrilling because, until then, the dinosaur had only been identified from scattered bones, many of which were lost during World War II. The new skull, which was about 1.6 millimeters long, gave scientists a much clearer idea of what this predator looked like. It was similar in size to the massive Giganotosaurus and even bigger than the famous Tyrannosaurus named Sue, whose skull measures around 1.53. Sereno and his team also made an intriguing observation. Carcharodontosaurus seemed to have had one of the largest skulls relative to its body size, while Tyrannosaurus likely had longer, more powerful legs. In 1995, Sereno spoke about these discoveries in an article titled "New Beast Usurps T-Rex as King Carnivore." He explained that these recently discovered dinosaurs from South America and Africa were putting up a challenge to Tyrannosaurus rex for the title of the largest and most fearsome meat-eating predator. Sereno believed that these findings were important because they were helping paleontologists better understand dinosaur communities during the late Cretaceous period, a time previously studied mainly in North America. However, in the same journal that reported on the Carcharodontosaurus discovery, another paleontologist, Philip J. Curry, offered a different perspective. He cautioned that it was still uncertain whether Carcharodontosaurus or Tyrannosaurus was truly the bigger predator. He stressed that in paleontology, size wasn't the most important detail. What mattered more were the adaptations of these creatures to their environments, their interactions with other species, and how they spread across different parts of the world. Curry also found it fascinating that two dinosaurs so closely related were discovered at nearly the same time, despite being found on opposite sides of the globe. In a 1997 interview, paleontologist Rodolfo Coria shared his estimate that Giganotosaurus was about 13.3 to 14.3 millimeters long and weighed between 8 to 10 tons. This made it bigger than another giant predator, Carcharodontosaurus. However, not all experts agreed. Paleontologist Paul Sereno voiced his concerns, pointing out that it was challenging to get an accurate size for the dinosaur when only a few partial fossils were available. Despite these disagreements, both Coria and Sereno agreed on one thing. The actual size of the dinosaur wasn't the most important thing to focus on. Instead, they believed it was more valuable to understand the unique features and characteristics of these ancient creatures. A year later, in 1998, an exciting breakthrough occurred. Jorge Calvo and Coria made a key discovery when they identified a partial left dentary bone, a piece of the lower jaw that had some teeth still attached, which they confidently attributed to Giganotosaurus. This bone, named MUVP95, had been collected by Calvo in 1988 near Los Candeleros, although it was originally found in 1987. In 1989, Calvo had briefly mentioned the bone and speculated that it might belong to an entirely new species of theropod dinosaur. Upon further analysis, Calvo and Coria were thrilled to find that the dentary bone closely matched the one from the first Giganotosaurus specimen, but this one was 8% larger, measuring a remarkable 24 in length. Even though the back part of the bone was missing, they made an exciting estimation. The skull of the original Giganotosaurus was probably about 1.8 meters long. However, for the larger specimen, they estimated the skull could have been a staggering 1.95 meters long, making it the longest skull of any known theropod dinosaur ever discovered. In 1999, a paleontologist named Calvo made an exciting discovery. He identified a partially preserved tooth known as MUVP52 as belonging to the giant dinosaur Giganotosaurus. This tooth had been found in 1987 by another researcher, A. Delgado, near Lake Ezequiel Ramos Mexia, making it the first known fossil of this enormous creature. Calvo also suggested that some huge dinosaur tracks, which he had first described in 1991 as belonging to a new species called Abalosaurus, might have been made by Giganotosaurus. These tracks were incredibly large, with some measuring about 20 in long, and the creatures that made them must have had strides as long as 51 in. Smaller tracks in the same area were about 14 in long, with a pace of 39 in. These tracks were triact, meaning they had 3 toes, and the impressions of the toes were deep and rough, showing sharp claws. In many of the tracks, the toes took up most of the space, and in one of them there was a clear mark of a thin heel. Even though these tracks were found higher up in the rock layers than the main fossils of Giganotosaurus, they were still from the same region where the tooth and other dinosaur fossils, including large sauropods, had also been discovered. This suggests that all of these creatures lived in the same area, providing more clues about the ancient world they inhabited. In 2001, a doctor-scientist named Frank Seebacker introduced a new way to estimate the body weight of dinosaurs. Instead of using vague guesses, his method used exact measurements of a dinosaur's body length, width, and depth to make a more accurate calculation. Using this technique on the powerful Giganotosaurus, Seebacker estimated that it weighed about 6.6 tons, based on its original length of about 12.5 meters. The next year, in 2002, 2 researchers, Coria and Curry, took a closer look at the Giganotosaurus, especially its skull. They found that the skull of the first discovered specimen, known as the holotype, was about 1.6 meters long. By measuring the femur, which had a circumference of 52 centimeters, they estimated that the dinosaur weighed around 4.2 tons. Their study also led them to calculate the Giganotosaurus's encephalization quotient, EQ, which is a measure of brain size compared to body size. They found the EQ to be 1.9, suggesting that its brain was relatively small compared to its huge body. In 2004, paleontologist Gerardo Fi Mazzetta and his team improved these weight estimates even more. They noticed that while the Giganotosaurus had a larger femur than the famous Tyrannosaurus rex Sioux, its tibia, a bone in the lower leg, was shorter by about 8 centimeters. Based on these measurements, Mazzetta's team concluded that the Giganotosaurus holotype was probably about the same size as Sioux, with an estimated weight of 8 tons. However, they guessed that a larger Giganotosaurus specimen with a bigger jawbone might have weighed as much as 10 tons. Using a mathematical technique called multivariate regression, they suggested that the holotype's weight was probably closer to 6.5 tons, while the bigger version could have weighed up to 8.2 tons. If this larger specimen existed, it would have made the Giganotosaurus the heaviest known carnivorous dinosaur on land at that time. In 2006, paleontologists Correa and Curry made another exciting discovery in Patagonia. They described Mapusaurus, a large theropod closely related to Giganotosaurus, which was about the same size. In 2007, paleontologists François Terrien and Donald M. Henderson carried out a detailed study of Giganotosaurus and its relatives. They concluded that Giganotosaurus reached around 13 meters long and weighed approximately 13.8 tons. They also found that Carcharodontosaurus, another massive carnivore, would have been around 13.3 meters long and weighed about 15.1 tons. This made both dinosaurs larger than the famous Tyrannosaurus rex. Therian and Henderson estimated that the skull of Giganotosaurus could have been as long as 1.56 meters. However, they warned that these measurements depended on the accuracy of the skull reconstructions, as the specimens they had were incomplete. They noted that better preserved fossils would help refine these estimates. Their research also suggested that dinosaurs like Giganotosaurus and Carcharodontosaurus had likely reached the maximum size possible for an animal that walked on 2 legs. In 2010, Gregory S. Paul, another expert in the field, further questioned the size of Carcharodontosaurid skulls, suggesting that they might have been reconstructed too long in general, adding yet another layer of complexity to the debate. In 2012, paleontologist Matthew T. Carano and his team took a close look at Giganotosaurus, a dinosaur famous for its enormous size. They noted that while the original specimen, the holotype, was fairly complete, there were still many parts of its skull that had not been studied in depth, aside from the brain case. They observed that several bones, especially where the skull bones would have connected, were missing. This made it difficult for them to figure out the full length of the skull. An interesting discovery they made was that the skulls of both Giganotosaurus and another giant, Carcharodontosaurus, were nearly the same size as the skull of the famous Tyrannosaurus rex. Carano's team also measured the femur, the thigh bone of the Giganotosaurus holotype. They found it to be about 4 ft long, which was slightly shorter than earlier measurements had suggested. This led them to think that Giganotosaurus was probably lighter and smaller than previously believed. In 2013, another paleontologist, Scott Hartman, took a different approach to studying the size of these giants. Using a technique called graphic double integration, Hartman created detailed drawings of dinosaur skeletons to estimate their weight. On his blog, he concluded that Tyrannosaurus rex, specifically the famous specimen known as Sioux, was larger than Giganotosaurus overall. Hartman estimated that the Giganotosaurus holotype weighed about 6.8 tons. In contrast, a bigger Giganotosaurus might have weighed around 8.2 tons, while Tyrannosaurus was estimated to weigh about 8.4 tons. Hartman also pointed out that, while the two dinosaurs might appear quite similar from the side, Tyrannosaurus had a wider torso. Hartmann also revisited a part of the Giganotosaurus jaw, which had been thought to be 8% larger than that of the holotype. Upon closer inspection, he concluded it was probably only about 6.5% larger. He even suggested that the jaw might belong to a different dinosaur of similar size, but with a stronger jaw. Hartmann acknowledged that since only one well-preserved Giganotosaurus specimen had been found so far, it was still possible that larger individuals could be discovered in the future. After all, it had taken nearly a century after the first discovery of Tyrannosaurus before the iconic Sioux specimen was unearthed. In 2019, another team, led by paleontologist W. Scott Persons, studied a massive Tyrannosaurus rex nicknamed Scotty. This discovery revealed that Scotty was not only larger but also heavier than other known giant theropods. However, the team suggested that some other theropods, like Giganotosaurus and Pteranodon, might have been even heavier. These dinosaurs had longer thigh bones, which hinted they could have had more muscle and body mass than Scotty. But because fewer fossils of these giants had been found, the researchers warned that future discoveries might reveal even larger specimens. They also pointed out that comparing the sizes of these giant dinosaurs was challenging because each species had unique features that made them different in shape. In 2021, paleontologist Matthias Reolid and his team decided to refine the calculations for the average weight of large theropods, including the mighty Giganotosaurus. They gathered multiple estimates and decided to exclude some numbers from 2007, which they thought were too extreme. This led to a new range for the weight of Giganotosaurus, putting it between 5.5 and 8.5 tons, with an average weight of around 6.75 tons. They also used advanced 3D models of the dinosaurs to estimate their body mass. For a 13-meter-long Giganotosaurus, they estimated that it could weigh as much as 7.2 tons, and these new findings were in line with earlier studies about its size. In 2022, another team of scientists, led by Juan Ignacio Canale, made a fascinating discovery about a large theropod called Meraxes, which was closely related to Giganotosaurus. They found a nearly complete skull of Meraxes that measured 1.27 meters in length. By comparing this skull to that of Giganotosaurus, they estimated that Giganotosaurus would have had an even larger skull, possibly reaching 1.63 meters in length, making it one of the largest theropod skulls ever discovered. Then, in 2023, paleontologist Henderson introduced a new method for estimating the size of incomplete dinosaur fossils by focusing on the pelvic region, which is often well preserved in fossils. He developed a more accurate way to predict the size of dinosaurs. Using this method, he calculated that Giganotosaurus was around 12.5 meters long, which matched the estimates from earlier studies conducted back in 1995. Giganotosaurus is thought to have been one of the largest meat-eating dinosaurs to ever roam the Earth. However, because only parts of its skeleton have been found, scientists have struggled to figure out just how big it was. This uncertainty makes it hard to say for sure if it was larger than the famous Tyrannosaurus rex, which has long been considered the largest known carnivorous dinosaur. Different researchers have come up with different estimates based on how they've reconstructed the missing pieces of its skeleton. Some believe the first discovered Giganotosaurus, known as the holotype, measured somewhere between 12 and 13 m long. Its skull is thought to have been about 1.53 to 1.8 min long, while its thigh bone, called the femur, was likely between 1.36 and 1.43 mm. The weight of this specimen could have ranged from 4.2 to 13.8 tons. The fact that its skull joints were fully fused suggests that this individual was fully grown when it lived. Another specimen, just a lower jaw from what may have been a larger Giganotosaurus, suggests it might have been around 13.2 meters long, with a skull measuring 1.95 meters and weighing about 8.2 tons. Some experts believe these higher size estimates might be too big. Many paleontologists picture Giganotosaurus as an exaggerated version of another famous dinosaur, Allosaurus. Although much of Giganotosaurus's skull remains a mystery, the parts that have been uncovered give us some clues about its appearance. From what's been found, it seems that it had a relatively low-profile head. The upper jaw, or maxilla, had a long row of teeth measuring about 92 centimeters and was deep from top to bottom, with nearly straight edges on both the upper and lower sides. It also had a noticeable bump just beneath the nostrils and a small, oval-shaped hole, similar to features found in both Allosaurus and Tyrannosaurus. The nasal bone was rough and bumpy, and this texture extended all over the top part of the skull. In front of the eye, the lacrimal bone had a rough ridge that slanted upwards and backward, with deep grooves along it. Behind the eye, the postorbital bone had a backward slanting extension that reached into the eye socket, similar to features seen in Tyrannosaurus and other theropods like Abelisaurus and Carnotaurus. Above the eye, the supraorbital bone formed a ridge connecting the lacrimal and postorbital bones, with a structure like that of Abelisaurus. The quadrate bone at the back of the skull was about 44 centimeters long and had two air-filled holes on its inner side. The top part of Giganotosaurus's skull, made of the frontal and parietal bones, was wide and created a shelf that hung over the short supratemporal fenestrae at the back of the skull. Unlike most theropods, the jaw of Giganotosaurus is attached further back from the occipital condyle, the point where the neck connects to the skull. The condyle was broad and low, with air-filled spaces inside. Giganotosaurus didn't have a sagittal crest, a ridge along the top of the skull, and its jaw muscles didn't spread onto the skull's roof, as they do in many other theropods. Instead, the muscles were connected to the lower sides of the skull's shelf. The muscles that helped raise the head were attached to the prominent supraoccipital bones on top of the skull, which worked like the nuchal crest, neck ridge, in tyrannosaurs. A latex endocast of Giganotosaurus's brain showed that its brain was similar in shape to that of its relative Carcharodontosaurus, but it was larger. The endocast measured 1 in, long, 3 in, wide, and had a volume of 9.7 fluid ounces. The lower jaw of Giganotosaurus had a dentary, front portion of the jaw, that became taller near the front, just where the two halves of the jaw met. The jaw was flattened in this area and had a downward projection at the tip, which some paleontologists have called a chin. The underside of the jaw was concave, while the outer side curved outward. A groove ran along the outer side, which housed small openings that provided nutrients to the teeth. On the inside of the jaw, there was a row of interdental plates, each with an opening for a tooth. The jaw had a groove called the Machelian groove along its bottom edge. The shape of the jaw suggests that Giganotosaurus had a wide mouth. It's believed that each side of the lower jaw had about 12 tooth sockets, each around 13 in. Long. Most of the teeth in the jaw were of similar size and shape, except for the first tooth, which was smaller. These teeth were compressed from side to side and had an oval cross-section with sharp serrations on the front and back edges, which is typical of theropods. The teeth had a curved S-shaped appearance when viewed from the front or back. One of its teeth had between 9 and 12 serrations per millimeter. The side teeth of Giganotosaurus had ridges of enamel, and the largest teeth at the front of the upper jaw had distinct wrinkles, especially near the serrations. Giganotosaurus had a powerful neck, with the axis bone, the vertebra that connects the neck to the skull, being especially strong. The vertebrae in the back of its neck were short and flat, with rounded, almost half-sphere-shaped joints at the front, These vertebrae also had hollow spaces called pleurocoels, divided by bony plates known as laminae. The back vertebrae were tall and had deep hollow spaces. Its tail vertebrae were unique, with long backward curving spines and thick vertebrae. The tailbones had long transverse processes, the parts that stick out sideways, and the chevrons at the front of the tail were shaped like blades. The shoulder area of the Giganotosaurus was shorter compared to that of the Tyrannosaurus. The ratio of the length of the shoulder blade, scapula, to the femur, thigh bone, was less than 0.5. The scapula had straight edges and a strong bump called a tuberosity, where the triceps muscle was attached. The coracoid, another bone in the shoulder, was small and hook-shaped. The pelvis, hip area, of Giganotosaurus had a rounded upper edge, a small blade behind the hip socket, acetabulum, and a narrow projection, brevis shelf, where muscles attached to the tail. The pubic foot, part of the pelvis, was shorter in the front than the back. The ischium, a pelvic bone, was straight and expanded backward, ending in a lobe-like shape. Its femur had a curved shape and a very strong upward-pointing head with a deep groove. The lesser trochanter, a bump on the femur, was wing-like and positioned below the greater trochanter, which was shorter. There was also a large fourth trochanter at the back of the femur. The tibia, or shin bone, was wider at the top, where it connected with the femur, and had a narrow, compressed shaft running down the front. This design helped support the massive weight of the Giganotosaurus and allowed it to move efficiently. In 2002, researchers Correa and Curry made an important discovery about Giganotosaurus. They found that the back part of its skull had certain features, like the forward slope of the occiput and the wide, low occipital condyle, which suggested the dinosaur had a great ability to move its head sideways. This movement was likely important for hunting and fighting, as it allowed Giganotosaurus to adjust its head quickly. These features could also be linked to the large and powerful muscles in the jaw. The way the jaw was connected to the skull was slightly different from other dinosaurs. It was positioned further back, which gave Giganotosaurus longer jaw muscles, helping it close its jaws faster. In contrast, Tyrannosaurus had more massive jaw muscles to give them a stronger bite force. In 2005, Therien and his team studied the bite force of various theropod dinosaurs. They found that Giganotosaurus and its relatives were built to deliver powerful bites to capture and kill prey. Tyrannosaurs, however, had evolved to better withstand twisting forces and break bones. The researchers couldn't give an exact number for the bite force, but it was clear that Giganotosaurus had a weaker bite compared to Tyrannosaurus. The bite force also decreases as you move towards the back of its mouth. The front part of the jaws was especially good for slicing through prey, suggesting that Giganotosaurus primarily used the front of its mouth to grab and handle its food. The shape of the lower jaw may have helped resist the stress of biting down with such force, especially when attacking large prey like young sauropods. This suggested that Giganotosaurus and similar dinosaurs were generalists, capable of hunting a variety of animals smaller than themselves. In 2006, fossils of a close relative, Mapusaurus, were discovered in a bone bed that contained the remains of several individuals at different stages of growth. In a National Geographic article the same year, Correa proposed that the bone bed likely resulted from a catastrophic event, and the fact that most of the fossils were from medium-sized individuals, with few younger or older ones, pointed to pack behavior. This could have been an advantage for hunting large sauropods, as working together in groups would have made it easier to bring down such massive prey. Scientists Correa and Salgado suggested that the massive size of theropods, including Giganotosaurus, might have evolved due to similarities in their environments or ecosystems. This phenomenon, known as convergent evolution, means different species developed similar traits because they faced comparable challenges in their surroundings. Another group of researchers, led by Sereno, discovered that a family of giant meat-eating dinosaurs, the Carcharodontosauridae, was widely spread across the world during the early Cretaceous period. These dinosaurs included Carcharodontosaurus in Africa, Acrocanthosaurus in North America, and Giganotosaurus in South America. However, as the Cretaceous period progressed, ocean barriers emerged, cutting off connections between continents. This separation led to distinct groups of dinosaurs evolving in isolation. For example, the northern continents became home to tyrannosaurs, South America had abelisaurids, and Africa continued to house Carcharodontosaurids. Giganotosaurus belonged to a subgroup of Carcharodontosaurids called Giganotosaurini. These dinosaurs thrived on the southern supercontinent, known as Gondwana, made up of South America and Africa. Here, they were likely the top predators. Within this group, Giganotosaurus and its close relatives formed a tribe called Giganotosaurini, which became separated from their African cousins when Gondwana began to break apart during the early Cretaceous period. Correa and Salgado also noticed that Giganotosaurus shared key features with a large group of advanced theropods called Tetanurae, such as similarities in their legs, skulls, and pelvises. These traits set it apart from more primitive theropods like Ceratosaurus. In 1996, Sereno and his team linked Giganotosaurus with Carcharodontosaurus and Acrocanthosaurus, placing them all in the same dinosaur family, Carcharodontosauridae. The three dinosaurs shared unique skull features, including a wide shelf of bone above their eyes and a squared-off front end of their lower jaws. Over time, as scientists discovered more Carcharodontosaurid fossils, they were able to map out their family tree more clearly. Paleontologist Thomas R. Holtz defined the group as all dinosaurs closer to Carcharodontosaurus than to Allosaurus or Synraptor. In 2006, Correa and Curry placed Giganotosaurus and its relative Mapusaurus into a subgroup called Giganotosaurini, based on specific traits in their thigh bones. Later, in 2008, Sereno and Stephen Brusate grouped Giganotosaurus, Mapusaurus, and another dinosaur, Tyrannotitan, into the tribe Giganotosaurini. With one of the most complete skeletons among its family, Giganotosaurus provides a wealth of information about the fearsome Carcharodontosauridae, offering valuable insights into their evolution, relationships, and dominance as apex predators of their time. Mapusaurus, which means earth lizard, was a massive carnivorous dinosaur that roamed Argentina during the late Cretaceous period, specifically in the Turonian age. This giant was part of the Carcharodontosauridae family, a group of fierce, meat-eating dinosaurs. Between 1997 and 2001, a team from the Argentinian-Canadian Dinosaur Project uncovered its fossils in the Huincal Formation, an area rich in prehistoric remains located at Cañadón del Gato. Paleontologists Rodolfo Correa and Phil Curry officially described and named Mapusaurus in 2006. The name Mapusaurus comes from the Mapuche language, where Mapu means of the land or of the earth, combined with the Greek word saurus, meaning lizard. The species name Mapusaurus roseae is a tribute to both the pinkish, rose-colored rocks where the fossils were discovered and to Rose Letwin, who generously supported the excavation efforts. The main fossil, called the holotype, is an isolated right nasal bone, which is displayed at the Museo Carmen Funes in Plaza Huincul. In total, 12 other fossils from different parts of the dinosaur skeleton, called paratypes, have been found, giving us a detailed picture of what Mapusaurus looked like. Mapusaurus was a large theropod, but it wasn't quite as massive as its close relative Giganotosaurus. The biggest Mapusaurus measured between 33 and 40 ft long and could weigh anywhere from 3 to 6 metric tons. Even though it wasn't the largest predator around, It was still an intimidating figure in the ancient world, ruling the landscape as one of the most formidable hunters of its time. Scientists have discovered that Mapusaurus can be identified by its unique traits, known as autapomorphies, in areas of its skeleton that Giganotosaurus does not have preserved. The only real difference between the two dinosaurs is that Mapusaurus lacks a second opening in the middle part of its quadrate bone and has small differences in the shape of its nasal features. Fossils of Mapusaurus were found in a bone bed, a site where many dinosaur remains are preserved together. This particular bone bed contains the remains of at least 7, and possibly as many as 9, Mapusaurus individuals of different ages. Paleontologists Correa and Curry suggested that these fossils might represent a collection of carcasses that accumulated over a long period, possibly due to some sort of predator trap. They believed that this bone bed could offer important clues about how Mapusaurus lived and behaved. Similar fossil sites have been found for other dinosaurs, such as the dromaeosaurid Deinonychus and Utahraptor, the large predatory Allosaurus, and various types of tyrannosaurs like Teratophonius, Albertosaurus, and Daspletosaurus. Rodolfo Correa, a paleontologist from the Museo Carmen Funes, who has previously written about this discovery, has said in press conferences that the large gathering of Mapusaurus fossils might indicate that these dinosaurs, like Giganotosaurus, hunted in groups. He speculates that they could have worked together to bring down giant prey, such as the massive sauropod Argentinosaurus. If this is true, it would be the first solid evidence that large theropods, other than the well-known Tyrannosaurus rex, might have hunted in packs. However, it's still unclear whether they hunted in a coordinated way, like wolves or lions, or if they simply attacked together in a chaotic mob. The fossils were found in the Huincul Formation at the Cañadón del Gato locality, a site where paleontologists believe a freshwater river or stream once flowed. The region would have been arid or semi-arid when these animals lived. This bone bed is especially important because fossilized bones are quite rare in this formation. Further studies on Mapusaurus show an interesting evolutionary feature known as heterochrony. This is when an animal keeps an ancestral trait during part of its life, but loses it as it grows. In Mapusaurus, younger individuals have certain openings in their skulls that disappear as they mature. Correa and Curry's detailed study showed that Mapusaurus is closely related to the group of dinosaurs known as Carcharodontosauridae. They found that the shape of the Mapusaurus femur indicates it is more closely linked to Giganotosaurus than to Carcharodontosaurus. Based on this discovery, they created a new group called Giganotosauridae, which includes all Carcharodontosauridae more closely related to Giganotosaurus and Mapusaurus than to Carcharodontosaurus. They also considered adding Tyrannotitan to this group, but were waiting for more information about its fossils before confirming its place. The Huincul Formation, where Mapusaurus fossils were found, is believed to have been a dry landscape with seasonal or temporary streams. This area dates back to around 97 to 93.5 million years ago. Fossils from this time are scarce, but Mapusaurus shared its environment with several giant sauropods, such as Argentinosaurus, Chubutisaurus, and Cathartosaura, all massive plant-eating dinosaurs. While 2 other giant carnivores, Meraxes and Tatanan, were also found in the same region. They lived in older rock layers than Mapusaurus, meaning they did not exist at the same time. Other theropods, such as the abelisaurid Scorpiovenata and Ilocalesia, also roamed the area. Fossilized pollen found in the Huincul Formation reveals that many types of plants lived there. Studies have shown the presence of hornworts, liverworts, ferns, and various types of trees and flowering plants, including conifers and cycads. along with some pollen that can't yet be classified. This formation is one of the most significant places for dinosaur fossils in Patagonia, preserving not only dinosaurs, but also fish, turtles, reptiles, and crocodiles. Most of the vertebrate fossils come from the lower and older layers of the formation, suggesting they were deposited first. Giganotosauridae, also known as shark-toothed lizards, was a group of massive meat-eating dinosaurs that roamed the Earth millions of years ago. The name comes from the Greek word carcharodon, and it perfectly describes their fearsome, serrated teeth, which resembled those of modern sharks. This family of dinosaurs was officially named in 1931 by the German paleontologist Ernst Stromer. Today, scientists classify them as part of the larger group of carnivorous dinosaurs known as Carnosauria. These giants were some of the most fearsome land predators to ever exist, rivaling even the legendary Tyrannosaurus rex in size. Among them were the colossal Giganotosaurus, Mapusaurus, Carcharodontosaurus, and Tyrannototon. The largest members of this group could weigh an astounding 8 to 10 metric tons, while the smallest still tipped the scales at a hefty 500 kilos. During the early and middle Cretaceous period, roughly 127 to 90 million years ago, Carcharodontosauridae dominated the land as apex predators, especially in the supercontinent Gondwana, which included what is now South America, Africa, and other southern regions. They also had a presence in North America, Europe, and Asia, with species like Acrocanthosaurus, Concavenator, and Shiochilong, respectively. Alongside the massive Spinosaurids, Carcharodontosauridae ruled their ecosystems, preying on other large dinosaurs. However, their reign wasn't permanent. By the end of the Turonian Age, about 90 million years ago, they began to vanish. In Gondwana, they were replaced by smaller but equally fearsome abelisaurids, while in North America and Asia, the rise of the tyrannosaurs marked the end of their dominance. Some fossilized teeth and bones discovered in South America were once thought to belong to Carcharodontosauridae from a later time, but closer examination revealed they were actually from abelisaurids. Interestingly, the origins of this family go back even further than the Cretaceous. In 2011, a discovery in Tanzania's Tendaguru Formation revealed Veterupristisaurus, the oldest known Carcharodontosaurid, which lived during the late Jurassic period, around 154 to 150 million years ago. This remarkable find pushed back the timeline of these fearsome predators, showing that their legacy began earlier than previously thought. The Carcharodontosauridae family was first named by a paleontologist named Ernst Stromer in 1931, when he discovered a new species called Carcharodontosaurus saharicus. This species was the first to belong to this family. Later, in 1995, another dinosaur called Giganotosaurus, which was closely related to Carcharodontosaurus, was added to the same family. Some scientists also believe that another dinosaur, Acrocanthosaurus, should be placed in this family based on certain similarities. However, other researchers think that Acrocanthosaurus belongs to a different family called Allosauridae. Carcharodontosaurids have some distinct features that make them unique. For example, the upper jaw has plates that are deeper than they are wide, and the front part of the lower jaw is square-shaped. Their teeth have wrinkled enamel, and they have 4 openings in the front of the upper jaw. The bones at the back of their neck are curved in a specific way, and their neck vertebrae are taller than their width. These dinosaurs also have large, rough areas on their skull, particularly around their eyes, which helped form a wide space for their eyes. Finally, their thigh bone has a unique angle that points slightly inward. In 2006, a discovery called Mapusaurus led scientists Rodolfo Coria and Phil Curry to create a new subfamily called Giganotosaurinae. They grouped the South American species of this family because they found that they were more closely related to each other than to the African or European species. Although they didn't include Tyrannotitan in this group right away, they suggested that it might belong there too, especially because of certain features in its thigh bone. In 1998, Paul Sereno introduced the term Carcharodontosauridae. This group includes Carcharodontosaurus and all species that are more closely related to it than to other dinosaurs like Allosaurus, Sinraptor, Monolophosaurus, or Cryolophosaurus. As a result, this group is considered separate from another group called Allosauridae. Bahariosaurus, another dinosaur, has been suggested to belong to the Carcharodontosauridae family, but scientists are unsure because the fossils they have are too incomplete to confirm this. Some researchers have also proposed that Carcharodontosauridae might be more closely related to Abelisauridae, another group of dinosaurs, rather than to Allosauridae. This idea comes from the fact that Carcharodontosauridae and Abelisauridae share similar features in their skulls. However, these similarities may be the result of parallel evolution, a process where different groups evolve similar traits independently due to similar environmental pressures. In contrast, a greater number of features in both the skull and the body suggest that Carcharodontosauridae are more closely related to Allosaurus than to Abelisauridae. Carcharodontosaurus, jagged-toothed lizard, was a massive meat-eating dinosaur that lived in what is now North Africa about 100 to 94 million years ago during the late Cretaceous period. The first fossil evidence of this dinosaur came from 2 teeth discovered in Algeria, which were originally thought to belong to a different species called Megalosaurus saharicus. These teeth were described in 1923 by French paleontologists Charles Desperey and Justin Savornin. A partial skeleton of Carcharodontosaurus was later found by German paleontologist Ernst Stromer during an expedition to Egypt in 1914. However, Stromer did not announce the discovery until 1931, giving the dinosaur its official name, Carcharodontosaurus, with the species name Saharicus. Sadly, this important skeleton was destroyed during World War II. Then, in 1995, nearly a century later, a nearly complete skull of C. saharicus was found in Morocco in the Kem beds. This new specimen was preserved well enough to become the official reference for the species in 1996. In 2007, additional fossils from northern Niger were discovered and named as a new species, C. iguidensis. Carcharodontosaurus was one of the largest meat-eating dinosaurs ever to roam the Earth. It grew to lengths of 33 to 41 ft and weighed between 4 to 7 metric tons. Its skull was large but light, with a triangular shape. Its powerful jaws were lined with sharp, curved teeth that had serrated edges similar to those of the great white shark. These teeth were the inspiration for the dinosaur's name. Though its skull was light, it had large openings in the bone, which made it more fragile compared to the skulls of other giant theropods, like the T-Rex. The front arms of Carcharodontosaurus were quite small, while its hind legs were strong and muscular. Like other theropods, it had a long tail that helped it keep balance while running. During this time, North Africa was home to a variety of giant theropods. Along with Carcharodontosaurus, there was the giant Spinosaurus, a possible Deltadromeus, and the mysterious Bahariosaurus. The region also had a large variety of fish, crocodiles, and flying reptiles, thriving in a landscape of mangrove forests and wetlands. Interestingly, despite its size and sharp teeth, studies show that Carcharodontosaurus had a bite force that, while still strong, was weaker compared to other theropod dinosaurs. Back in 1924, 2 fossilized teeth of a massive dinosaur called Carcharodontosaurus were discovered in cuts along ancient irrigation tunnels known as fogaras near Timimoun in what was then French Algeria. These teeth were found in rock layers from the Cretaceous period, specifically part of the continental intercalaire formation. The fossils were handed over to the governor of Timimoun, Captain Berthe, who passed them on to a French geologist, Charles Desperey. Later that year, in 1925, Desperey and his colleague Justin Savornin studied the teeth and identified them as belonging to a new species of large meat-eating dinosaur. They named it Megalosaurus saharicus, with Saharicus referencing the Sahara Desert where the fossils were found. This was a big deal because it marked the first time a theropod dinosaur, a group of two-legged carnivorous dinosaurs, had been described from the region. However, the genus Megalosaurus had become something of a catch-all category for theropod fossils that scientists didn't fully understand, and many species were added to it without much evidence. This included M. saharicus, which in 1927 was even briefly classified as part of another dinosaur genus, Dryptosaurus, although this turned out to be incorrect. To add to the confusion, another German paleontologist, Friedrich von Huene, mistakenly named a different dinosaur species from the region, Megalosaurus africanus, but it was later considered the same as M. saharicus. Unfortunately, the original two teeth that Desperey and Savornin used to name the species have since gone missing. It's believed they might still be in collections somewhere in Algeria, Paris, or Lyon, but they haven't been located. Adding to the challenge, the teeth didn't have unique features that could easily set them apart from other dinosaurs in the Carcharodontosauridae family. In 1960, French paleontologist Albert Félix de Lapparent reported finding more fossils in Algeria, including additional teeth and tailbones, which he linked to Carcharodontosaurus. However, some of these fossils might belong to different types of dinosaurs. Over time, more teeth and isolated fossils have been uncovered in various parts of Algeria, shedding light on the presence of these incredible predators in North Africa millions of years ago. The story of Carcharodontosaurus saharicus begins in the spring of 1914 in the desert near Aphrodite, Egypt. Here, Austro-Hungarian paleontologist Richard Markgraf unearthed fossils from a rock layer called marl. These marls belong to the Bahariya Formation, a geological treasure trove from the Cenomanian age of the late Cretaceous period, located in North Africa. Markgraf was not working alone. He was gathering fossils for Ernst Stromer, a German paleontologist associated with the Bavarian State Collection of Paleontology in Munich. Markgraf's efforts uncovered a fascinating collection of bones belonging to Carcharodontosaurus saharicus. This partial skeleton, catalogued as IPHG 1922-X46, included parts of the skull, notably much of the brain case, several teeth, neck and tail vertebrae, pieces of the pelvis, a claw, thigh bones, and the left fibula. There was also an isolated ilium, a part of the hip, but later studies suggested it belonged to a different type of dinosaur, possibly an etosaur. However, transporting these fossils to Germany proved to be a significant challenge due to political tensions between the German Empire and Egypt, which was under British control at the time. It wasn't until 1922 that the fossils finally made their way to Munich. There, Stromer studied them in detail, and by 1931, he officially described the species. Stromer noted that the teeth of this dinosaur were strikingly similar to those of the great white shark, Carcharodon carcharias, with their razor-sharp edges and serrations. This resemblance inspired him to create a new genus for the species, naming it Carcharodontosaurus, which means shark-toothed lizard. However, the fossil's story took a darker turn during World War II. In April 1944, during a British bombing raid on Munich, the original fossils of IPHG 1922-X46, along with many other specimens from Bahariya, were destroyed. The only piece of this remarkable discovery that survived was an endocast, a model of the brain case that had been made before the war. This lone relic remains a vital connection to one of the most fearsome carnivores to ever roam the ancient landscapes of North Africa. Until 1995, discoveries related to Giganotosaurus, a massive and terrifying predator from the Cretaceous period, were extremely rare. That changed when American paleontologist Paul Sereno and his team from the University of Chicago stumbled upon a partial skull during an expedition. This remarkable find, labeled as UCRC PV12, came from rocks dating back to the Cenomanian age, found in the lower Douira formation of the Kem beds in southeastern Morocco near Erfoud. Once the specimen was transported to the University of Chicago, it was described in detail by Sereno and his colleagues in 1996. Interestingly, this particular skull would later gain significant importance because older specimens of Giganotosaurus saharicus had been lost over time. UCRC PV12 was designated as the neotype of the species, which means it became the new reference point for identifying C. saharicus, thanks to its similar age and location to the lost fossils. However, its designation sparked debate. In 2016, researchers Kirensa and Cao pointed out differences in the structure of the maxillary interdental plates, parts of the upper jaw, between the neotype and the original holotype. On the other hand, paleontologist Mickey Mortimer argued that these differences were simply due to damage to the new specimen, not true anatomical variations. Over the years, other fossils of C. saharicus have been uncovered in the Kem beds. These include parts of the lower jaw, neck vertebrae, and numerous teeth, further enriching our understanding of this prehistoric giant. At one point, Sereno and his team suggested that certain stout neck vertebrae, previously attributed to spinosaurid dinosaurs like Giganotosaurus and Spinosaurus, might belong to Giganotosaurus. They reasoned that a predator with such a large and powerful skull would need strong neck bones to support it. However, later studies by Ibrahim and colleagues in 2020 reassigned these vertebrae back to Spinosaurus aegyptiacus, clarifying the confusion. Interestingly, French paleontologist René Lavocat had already hinted at the presence of Giganotosaurus in Morocco back in 1954. This early observation laid the groundwork for what would eventually become one of the most fascinating chapters in the study of prehistoric predators. Today, Giganotosaurus remains a symbol of ancient terror, capturing the imagination of paleontologists and dinosaur enthusiasts alike. In 2007, paleontologists Steve Brusatte and Paul Sereno introduced a new species of Giganotosaurus, naming it C. iguidensis. The discovery was based on fossils found during an expedition to the Echkar Formation in Idai, Niger. The most important fossil, a partial upper jawbone known as a maxilla and labeled MNN-IGU2, was chosen as the holotype, which means it became the official specimen representing the species. The species name, iguidensis, honors the place where the fossils were discovered. Alongside the holotype, other fossils, including parts of the skull like a brain case, and lacrimal bone, pieces of the lower jaw, a dentary, neck vertebrae, and several teeth were tentatively linked to C. iguidensis. These were grouped because they were similar in size and shape to other Giganotosaurus fossils. However, later studies in 2016 by researchers Kirensa and Cao raised doubts. They concluded that some of these additional bones likely belonged to a different dinosaur, Giganotosaurus, later thought to be a type of Spinosaurus, or to unrelated dinosaurs. As a result, they suggested that C. iguidensis should only be identified by its holotype until more evidence is found. Another fascinating find came from Morocco's Kem beds in 2012. A new Giganotosaurus species called Sauroniops pachythalus. This species was based on a single skull bone, a frontal, which led to debates among scientists about whether it was truly a distinct species or another member of the Carcharodontosauridae family. But this idea has not gained widespread acceptance. There's also been some confusion about Giganotosaurus, a famous South American predator. In 1998 and 2010, some paleontologists suggested that Giganotosaurus was just a synonym for Carcharodontosaurus. However, this claim hasn't been supported in more recent research, and the two remain classified as separate species. Stromer suggested that Carcharodontosaurus saharicus was likely about the same size as the tyrannosaurid Gorgosaurus, meaning it could have been around 8 to 9 meter long, based on his fossil specimen IPHG 1922X46. This specimen was about 15% smaller than the neotype, which was estimated to be between 12 to 12.5 millimeters long and weighing about 5 to 7 metric tons. This places C. saharicus among the largest known theropods and land carnivores, making it the second largest Carcharodontosaurid and the third largest theropod overall by most estimates. In contrast, C. iguidensis was much smaller, reaching only about 10 millimeters long and weighing 4 metric tons. The biggest and most complete skull of C. saharicus would have measured around 1.6 millimeters long when fully preserved, which is comparable to the largest skulls of Tyrannosaurus. However, no skulls of Carcharodontosaurus have been found that include the complete premaxilla, front jawbone, back sections, or the lower jaw. The skulls of Carcharodontosaurus, like C. saharicus, tend to be narrower and lighter than the thicker, stronger skulls of later tyrannosaurs, which were adapted for crushing prey. The neotype skull of C. saharicus tapers to a point at the front, giving it a triangular shape in side view, similar to other Carcharodontosaurids like Mapusaurus and Giganotosaurus. Its skull was lighter than that of tyrannosaurs, with the anteorbital fenestra, the large hole in the skull in front of the eyes, making up over 30% of the total skull length. This fenestra is surrounded by shallow depressions in the maxilla, upper jaw, nasals, nose bone, jugal, cheekbones, and lacrimals, front orbit bones. Like other members of its family, the nasal bone of C. saharicus is elongated and has a rough, bumpy surface at the front, which would have been covered by keratin to form a horn-like structure similar to what is seen in Ceratosaurus. A similar rough texture can also be found on the lacrimal bone, which would have been extended by keratin to create a similar feature. The most unique feature of Carcharodontosaurus's skull is the sculpted surface of the maxilla, a characteristic that distinguishes it from other dinosaurs. On the other hand, C. iguidensis has different features such as anteorbital fossae, located closer to the anteorbital fenestra, a crest on the inner face of the maxilla, and a process along its midline features that are absent in C. saharicus, helping to separate the two species. The maxilla of the IPHG 1922X46 specimen was about 70 cm long when complete, while the neotype's maxilla is much larger, with 14 tooth sockets in each maxilla. Although parts of the brain case have been found, they resemble those of Giganotosaurus in many ways. However, C. saharicus has a more prominent nuchal crest, a bony ridge that juts out over the back of the skull. The frontal bones in the skull are fused, which is typical of most theropods. The jugals are wide and shaped like triangles. The articulation of the lower jaw is located farther back compared to most theropods, positioned just behind the occipital condyle, the joint where the skull meets the neck. Additionally, it includes 30 teeth in the lower jaw, 8 in the front of the upper jaw, premaxillary, and 24 in the upper jaw itself, maxillary. The teeth of Carcharodontosauridae have serrations on the edges of teeth from C. saharicus and up to 32 serrations per semillose in C. iguidensis. The teeth were straight and flat from side to side, with a tapered spindle-like shape when looked at from the front. Towards the back of the mouth, the teeth became more curved. The back edges of these teeth were not only curved, but also had a smooth, convex shape. The crowns of the teeth had ridges of enamel running across them, curving towards the serrated edges, forming a band-like pattern along the tip. In 2001, researcher Hans C. E. Larsen studied the inner ear and brain structure of Giganotosaurus saharicus. He found that the brain of this dinosaur was divided into three parts: the forebrain, the midbrain, and the hindbrain. The forebrain was located near the tip of the snout, followed by the midbrain, which was tilted down at a 45-degree angle toward the back of the animal. The hindbrain was positioned almost parallel to the forebrain and angled about 40 degrees relative to the midbrain. The overall brain structure of C. saharicus was similar to that of another dinosaur, Allosaurus fragilis. Larsen also noted that the cerebrum, the part of the brain responsible for higher functions, was in a typical proportion to the rest of the brain for a non-avian reptile. Additionally, Giganotosaurus had a notably large optic nerve, suggesting it had keen vision. The inner ear of Giganotosaurus saharicus had three semicircular canals that, when seen from the side, formed a shape similar to a triangle with rounded corners. This triangular shape is also found in other ancient creatures like Allosaurus, lizards, and turtles, but not in birds. The canals themselves were very straight, which explains the sharp shape they created in life. Part of the brain, called the floccular lobe, would have extended into the area surrounded by these canals, much like it does in other dinosaurs, birds, and flying reptiles called pterosaurs. Not much is known about the bones of Giganotosaurus outside of its skull. Many isolated bones found in the Sahara have been linked to this dinosaur, but they haven't been studied in great detail. Like other members of the Giganotosauridae family, Giganotosaurus had a strong, muscular body with relatively small arms, a long tail, and a short neck. The most complete specimen ever found was destroyed, but it once included 3 neck, cervical vertebrae, which had been severely weathered over time. One of them was an axis vertebra, and the other 2 were larger and wider connecting vertebrae that made up the front part of the neck. The neck bones were thick and had concave, curved inward ends, like in Giganotosaurus. The tops of the neck bones were flat and had small spines that connected to strong, horizontal bone extensions. These extensions were likely connected to air sacs inside the vertebrae, which helped make the bones lighter. The bottoms of these bones also had ridges or keels along their underside. One of the tail vertebrae found was short and had flat ends, a trait known as platycoli. It was missing parts of its spine, but still had structures that would connect to the tail's chevron bones. The sides of its centrum, the main part of the vertebra, also had air sac cavities. 2 chevron bones, which helped protect the tail, were preserved with this specimen. The pelvis of Giganotosaurus was mostly incomplete, but it included parts like the pubic bones and the left ischium. These bones, found in related species, show that the pelvis had a distinctive shape. The pubes pointed forward and the ischium pointed backward, which is a common feature of all Saurischian dinosaurs. When fully intact, the pubic bones would have been nearly 1 meter long. The front ends of the pubes were wider and formed a V shape when viewed from the front. 2 femurs, thigh bones, and the left fibula, a smaller leg bone, were also found. The femur was one of the largest ever recorded for a theropod, measuring 1.26 meters long. It was mostly straight with a slight curve at the ends. The femur had a small bony bump, called the greater trochanter, which would have connected to the muscle that helped move the tail. The fibula was much shorter, about 1/3 the length of the femur, measuring 88 centimeters. The front end of the fibula had a triangular shape, and the back end was rounded. The teeth of Carcharodontosaurus, like Allosaurus's, are unique with their thin, blade-like structure. These teeth, though sharp, are fragile and could break or bend if they struck something hard, such as bone. The straight edges, slightly curved tips, and wavy shapes of the teeth make them even more vulnerable to damage under pressure. However, compared to smaller theropods, these teeth are still much stronger, and their larger size allows them to withstand more force. Carcharodontosaurus also had a fast tooth replacement rate, so if a tooth was damaged, it could easily grow back. This is quite different from modern bone-crushing mammals, which spend a lot of energy maintaining their teeth. Evidence of bone-crushing behavior can be found in Allosaurus, which would engage in face-biting contests with other members of its species and bite the pelvic bones of Stegosaurus, leaving distinctive bite marks. Researchers have studied the bite forces of giant theropods, including Carcharodontosaurus, Acrocanthosaurus, and Tyrannosaurus. These studies show that Carcharodontosaurus had much weaker bite forces than Tyrannosaurus, even though they were similar in size. A study in 2022 estimated that the bite force of Carcharodontosaurus in the front of its mouth was 11,312 newtons, while the force in the back of its mouth was 2,149 newtons. This is much less than the bite force of Tyrannosaurus, suggesting that Carcharodontosaurus didn't eat bones. Further research on the skulls of these theropods has supported this idea. The bones of Carcharodontosaurus, Spinosaurus, and Acrocanthosaurus experienced a lot of stress in the back part of their skulls, near the jaw joint, indicating their skulls were not as solid as smaller theropods. The larger theropods, like Carcharodontosaurus, had big air pockets in their skulls to make them lighter, which made them less stable. However, Spinosaurus and Suchomimus had even more stress in their skulls, which suggests they could only eat small, soft prey, while Carcharodontosaurus was able to bite harder food thanks to its stronger skull. Isotope analysis of Carcharodontosaurus teeth has revealed that their oxygen isotope levels were higher than those of Spinosaurus, which suggests that Carcharodontosaurus lived on land, while Spinosaurus likely spent more time in the water. This is also supported by the fact that Carcharodontosaurus teeth are more often found in land-based environments than aquatic ones. Additionally, Carcharodontosaurus is believed to have had thermophysiology similar to endotherms, meaning it regulated its body temperature like warm-blooded animals. This was inferred from the isotopic data, which suggests Carcharodontosaurus primarily obtained water from drinking rather than from living in aquatic environments. Tyrannotitan is the name of a large meat-eating dinosaur that walked on two legs. It belonged to the Carcharodontosauridae family, a group of fierce predators, and lived during the early Cretaceous period, specifically in the Aptian stage. The dinosaur was discovered in Argentina, and it is closely related to other giant predators like Carcharodontosaurus, Giganotosaurus, and Mapusaurus. Tyrannotitan chubutensis was officially named and described by scientists Fernando E. Novas, Silvina de Valle, Pat Vickers-Rich, and Tom Rich in 2005. The fossils were found at La Anita Farm, located about 28 kilometers northeast of Paso de Indios in Chubut province, Argentina. These fossils are thought to be from the Cerro Castaño member of the Cerro Barcino Formation, which dates back to the Aptian stage of the early Cretaceous. The main fossil specimen, known as the holotype, was given the designation MPEFPV 1156. It includes many important remains, such as pieces of the jaw, teeth, back vertebrae, part of the tail vertebrae, ribs and chevrons, tailbone fragments, a partial shoulder blade, upper arm bone, humerus forearm bone, ulna, part of the pelvis ilium, a nearly complete thigh bone femur, fibula calf bone and left second toe bone. Metatarsal 2 In addition to the holotype, more fossils were found and labeled MPEFPV 1157. This includes parts of the jaw, jugulars, a right lower jaw, teeth, neck vertebrae, extra back vertebrae, fused sacral vertebrae, 5 bones joined together, some tail vertebrae, ribs, a right thigh bone, femur, a fragment of the left second toe bone, and several toe bones from the feet. These additional fossils help scientists learn more about the Tyrannotitan's appearance and movements. Tyrannotitan was a massive dinosaur, measuring between 12.2 and 13 mm in length and weighing around 4.8 to 7 tons. Its spine was unique, with many sections having air-filled spaces, similar to what we see in other large predators like Giganotosaurus and Mapusaurus. What makes Tyrannotitan particularly interesting is that it had an unusual air gap in the front part of its sacral hip area, where the normal flow of air through the spine was interrupted. This gap was caused by different parts of its respiratory system, like air sacs, which connected to specific sections of the vertebrae. This kind of gap is more commonly seen in younger dinosaurs, whose air sac system wasn't fully developed yet. It's a fascinating feature that gives us clues about how this enormous creature might have breathed and moved. The scapular coracoid, the bone that connects the shoulder blade and collarbone, is fused and much more developed compared to that of Giganotosaurus carolini. Although the arm is very small, most of the scapula's shaft is missing. The acromion, a part of the shoulder blade, curves about 90 degrees from the main shaft, giving it a shape that looks somewhat similar to the shoulder of a T-Rex. It's still unclear whether the differences between these species are due to evolution or sexual dimorphism, physical differences between males and females in a species, though the latter seems unlikely due to limited samples from both species. The vertebra near the base of the tail has a very tall neural spine, about twice as high as the body of the vertebra itself. The base of the eye socket, orbital fenestra, shows a sharp notch nearly 90 degrees deep into the side of the cheekbone, jugal, which is different from the rounded shape seen in Giganotosaurus, but similar to what's found in Carcharodontosaurus. The teeth have chisel-like serrations, similar to other Carcharodontosaurids. They also feature a wrinkled enamel surface and sharp edges on both the front and back sides of the teeth, and the crowns are flattened from side to side. The femur thigh bone of the paratype specimen measures about 1.4 m long, as reported by Novus et al. According to Canale et al., Tyrannotitan is considered a very early member of the Giganotosaurini tribe, which also includes Giganotosaurus. Characteristics shared by all members of the Giganotosaurini tribe include a postorbital process, a projection behind the eye socket on the cheekbone, a wide base for this process, and a special femur with a weak fourth trochanter, a bony bump, and a shallow broad groove on the lower end for muscle attachment. Torvosaurus, meaning bull hunter, was a massive predator from a group of dinosaurs known as Carcharodontosauridae. It roamed what is now Argentina during the Cenomanian stage of the late Cretaceous period, about 100 million years ago. This dinosaur was named after its impressive size and hunting prowess, with its name derived from the Latin words taurus, bull, and venator, hunter. So far, scientists have identified only one species of Torvosaurus, called T. violante. The first discovery of Torvosaurus happened in 2005 when a fossil, identified as a right post-orbital bone, part of the skull near the eye, was unearthed on the Violante farm in Rio Negro province, Argentina. This fossil, officially labeled as MPCA-PV82, came from the Huincal Formation, a region famous for its abundance of dinosaur fossils. Matthias Motta, the paleontologist who made the find, revealed that Torvosaurus shared its habitat with other fascinating dinosaurs like the Megaraptor and Aeoniraptor, some abelisauroids, and even a possible unenlagged Paravian, a smaller bird-like dinosaur. Nearly 2 decades later, in 2024, a second Torvosaurus specimen was described. This find, labeled MPCA PV83, included a partial skull, parts of the neck vertebrae, some ribs, fragments of forelimbs, a femur, parts of a foot, and a tailbone. Interestingly, this specimen was discovered in 2016, but was initially classified as indeterminate. Upon closer examination, scientists realized it belonged to Torvosaurus due to shared features with the original fossil and the fact that it was found just 800 meters away from the first discovery site. Torvosaurus was a giant, though not the largest in its family. Based on its femur size, scientists estimate it weighed around 5,628 kilos. This made it smaller than the colossal Giganotosaurus, which weighed about 6,349 kilograms, but larger than its relatives Mapusaurus and Meraxes, which weighed just over 4,300 kilos. Its skull, though incomplete, was estimated to measure an impressive 135 centimeters in length. The dinosaur's name also pays tribute to Enzo Violante, the owner of the farm where the fossils were discovered, further linking Torvosaurus to the region's rich paleontological history. The first skeleton of Torvosaurus showed some amazing features that made it stand out from other Carcharodontosaurid dinosaurs. One of the most noticeable traits was part of the bone above its eye, which was rough and stuck out like a small horn. This was very different from the smoother, more rounded bumps above the eyes of other dinosaurs in its family. Scientists like Motta and Rolando described this as a special feature of Torvosaurus. However, its close relative Meraxes also has a similar horn-like bone that sticks out to the side. Another interesting detail of Torvosaurus was in its neck bones. Some of its neck vertebrae, bones C3 to C6, had tall blade-like ridges called neural spines with tips that flared out at the top. These spines locked together like overlapping roof tiles, creating what scientists call a cervical complex. A somewhat similar feature exists in the neck bones of an older relative, Acrocanthosaurus, but the version in Torvosaurus was much more noticeable. Based on other Carcharodontosaurids like Giganotosaurus and Mapusaurus, researchers think this cervical complex might be a special trait of this group of dinosaurs. The cervical complex likely made the Torvosaurus's neck less flexible, but much stronger at the same time. Its skull had an interesting feature, a rounded joint at the back of the skull, called the occipital condyle, which allowed a lot of movement where the skull connected to the first neck bone. This design is similar to what we see in horned dinosaurs like Triceratops. It suggests that Torvosaurus's neck was not only strong, but also specially designed to support and move its heavy skull. The cervical complex likely made the front of the neck stronger and more stable, helping to anchor large neck and head muscles. This may have helped the dinosaur hunt and control struggling prey. It's a bit like the fused neck bones of horned dinosaurs, which serve a similar purpose. As for its back, only a few of Torvosaurus's mid-back vertebrae have been found. One of these bones has an unusually tall arch, standing 52 centimeters high, showing that this predator was built with great power. These special body features show Torvosaurus as a predator made for strength, stability, and accuracy, making it an exciting discovery in the world of dinosaurs. Torvosaurus stands out among its relatives for having the smallest arms ever found in any known allosauroid dinosaur. These arms were nearly completely preserved, showing a remarkable degree of reduction, even compared to other members of its family, like the similarly small-armed Meraxes. This reduction was especially noticeable in the forearms, which were proportionately smaller than usual. However, despite their size, Torvosaurus's forearms were surprisingly sturdy, and its fingers were highly flexible. Even so, like other Giganotosaurini, its forelimbs were not built for a wide range of movement and likely had limited functionality. Another fascinating feature Torvosaurus shares with Meraxes is an enlarged claw on its second toe. This claw was about 20% longer than the equivalent bone of its third toe and was more compressed from the sides, giving it a distinctive look. This unique adaptation might have played a role in hunting or defense. When it comes to its evolutionary position, scientists have compared Torvosaurus to other famous giants like Giganotosaurus, Carcharodontosaurus, and Mapusaurus. Initially, researchers suggested that Torvosaurus had a specialized place in the Carcharodontosauridae family tree, but later studies stirred up debate. In 2019, Correa and colleagues proposed that Torvosaurus might be the same dinosaur as Mapusaurus. They pointed out similarities, like the curved edges of a skull bone called the palatal, and other shared features. However, one key difference lies in where these two dinosaurs were found. Torvosaurus comes from the lower part of the Huincul Formation, while Mapusaurus is from the upper layers, indicating they might not have lived at the same time. In 2024, a new study led by Rolando supported the idea that Torvosaurus is a distinct species. They highlighted that its unique traits preserved in the fossil record were more pronounced than in any other member of its family. They also suggested that the curved palatal edge was not exclusive to these two dinosaurs, but might have been a common feature among Carcharodontosaurids. This ongoing debate keeps Torvosaurus's story exciting and its place in history intriguing. To better understand how Torvosaurus is classified using new fossil discoveries, researchers used a detailed set of data originally made for studying another dinosaur called Meraxes, adding a bit more information to improve their study. The fossils of Torvosaurus were found in the Huincul Formation, a well-known site in Argentina famous for its large collection of dinosaur remains. This area has produced fossils of two other big meat-eating dinosaurs from the same family, Mapusaurus and Meraxes. However, these huge predators were found in different rock layers, meaning they lived at different times and likely never met. The Huincul Formation is also home to many other meat-eating dinosaurs. These include the bird-like Oviraptor, the slender Huinculsaurus, and the fierce abelisaurids like Scorpiovenata, Tulosaurus, and Elocalesia. Another noteworthy predator from this area is the mysterious Aeoniraptor, part of the Megaraptoridae group, known for their sharp claws and quick movements. When it comes to plant-eating dinosaurs, the area is full of sauropods, the gentle giants of the dinosaur world. These include long-necked species like Cathartosaura and Limesaurus from the Rebbachisauridae family, as well as the enormous Argentinosaurus, Chubutisaurus, and Chucarosaurus, all part of the Titanosaur group. Fossils of plant-eating ornithischians are much rarer in the Huincul Formation. However, scientists have found a few, such as an unnamed iguanodon species and a rare dinosaur called Chakisaurus, which was part of the smaller, quick-moving Elasmarian group. This incredible variety of dinosaurs gives us a clear picture of an ancient ecosystem where giant predators lived alongside plant-eating giants, while smaller dinosaurs played their special roles. Each fossil found at this site helped scientists put together the amazing story of life from millions of years ago. Meraxes is the name given to a large, fearsome dinosaur that lived during the late Cretaceous period, around 70 million years ago, in what is now Patagonia, Argentina. This dinosaur belongs to a group called Carcharodontosauridae, known for its enormous size and sharp teeth, and Meraxes is one of the most impressive of its kind. The only species of this genus is Meraxes gigas. In 2012, paleontologists made a remarkable discovery when they found the remains of this dinosaur. The specimen, known as MMCH-PV65, was found to include a nearly complete skull, parts of the chest and hip bones, a few fragments of its forelimbs, and nearly whole hind limbs. Additionally, the remains included several vertebrae from its back and neck, as well as parts of its tail. This discovery is incredibly important because it represents the most complete Carcharodontosaurid skeleton ever found in the southern hemisphere. Before scientists officially described it as a new species in 2022, the specimen was simply called the Campanus carcharodontosaurid, after the area where it was found. This find helps us understand more about these terrifying large predators that once roamed the earth. Meraxes gigas, a huge dinosaur, was officially named in 2022 by Canale and his team after studying its remains. The name Meraxes honors a strong female dragon from the A Song of Ice and Fire books by George R.R. Martin, who was ridden by Queen Rhaenys Targaryen. The species name gigas comes from the Greek word for giant, emphasizing the dinosaur's enormous size. Meraxes is considered one of the largest meat-eating dinosaurs, weighing around 4.26 metric tons. In 2023, Henderson gave an estimated body length of 9 to 10 mpl, based on the research of Canale and his team. However, Henderson also suggested it might have been even bigger, estimating a length of 10.2 to 11.6 meters by looking at the dinosaur's pelvic area. Its skull was about 1.27 meters long, which is similar in size to that of the Acrocanthosaurus, another huge meat-eating dinosaur, which had a skull measuring between 1.23 and 1.29 meters. The shape and size of several bones, including the skull, shoulder blades, scapula, hand bones, metacarpals, and feet, suggest that Meraxes had similar proportions and body structure to Acrocanthosaurus. One of the most noticeable features of Meraxes was its unusually small front limbs, a result of convergent evolution. This means that 4 different groups of meat-eating dinosaurs, Carcharodontosauridae, Abelisauridae, Tyrannosauridae, and Alvarezsauridae, independently developed small front limbs over time. Meraxes also had a unique second toe, which had a large claw, nearly twice as long as the claw on its 4th toe, adding to its unusual and frightening appearance. Analysis of the bones of the holotype suggests that this individual of Meraxes likely lived to be between 39 and 53 years old, having reached full skeletal maturity around 4 years before its death, at about 35 to 49 years old. This would make Meraxes the longest living non-avian theropod ever discovered. Unlike the faster-growing Tyrannosaurus, which reached its large size through rapid growth, Meraxes grew to its massive size more gradually by extending its growth period, a process called hypermorphosis, rather than speeding up its growth rate, acceleration. A study in 2022 by Canale and colleagues placed Meraxes as the earliest branch of the Giganotosauridae tribe, a group within the larger Carcharodontosauridae family. The fossilized remains of Meraxes were found in the Huincul Formation, a rich site that also contained many other prehistoric creatures. Theropods from this area include the Paravian Oviraptor, the Alvarezsaurid Huinculsaurus, and Abelisaurids like Scorpiovenator, Tulosaurus, and Ilocalicia. Additionally, Meraxes shares its environment with the megaraptorid Aeoniraptor, as well as other giant Carcharodontosaurids like Mapusaurus and Torvosaurus. Since Meraxes was found in an older rock layer than Mapusaurus and Torvosaurus, it is unlikely that they lived at the same time. The herbivores in this area included large sauropods like Cathartosaura and Limesaurus, titanosaurids such as Argentinosaurus, Chubutisaurus, and Chukarosaurus, as well as various types of iguanodonts, though some of these species are less clearly identified. Acrocanthosaurus was a large and frightening dinosaur that lived in North America around 110 to 113 million years ago during the early Cretaceous period. This meat-eating dinosaur, part of the Carcharodontosauridae family, is known from fossil remains found over a wide area, including the US states of Oklahoma, Texas, Wyoming, and even Maryland in the east. This giant predator stood tall on 2 strong legs, making it a 2-legged hunter. It is most famous for its unique high spines on its back. These spines, which rose from many of its bones, likely supported a ridge of muscle along its neck, back and hips, giving it a special and scary look. The largest known Acrocanthosaurus measured about 36 to 38 ft long and could have weighed up to 7 tons, making it one of the largest meat-eating dinosaurs in its environment. Fossilized footprints found in Texas suggest that this predator might have left its mark there, although no direct connection to its skeleton has been confirmed. Recent discoveries have provided new information on its body, including studies of its brain and the way its front limbs work. Acrocanthosaurus was a top predator in its ecosystem, likely hunting large plant-eating dinosaurs like sauropods, ornithopods, and ankylosaurs. The name Acrocanthosaurus comes from the Greek words acra, meaning high, acantha, thorn or spine, and saurus, lizard, referring to the tall spines on its back. The species name Atokensis was chosen after the place where the first fossils were found, Atoka County in Oklahoma. The dinosaur was first named and described in 1950 by paleontologists J. Willis Stovall and Juan Langston Jr. The first major fossils of Acrocanthosaurus were discovered in the early 1940s, including partial skeletons and skull pieces from the Antlers Formation in Oklahoma. In the 1990s, more complete specimens were found, including a nearly complete skeleton from Texas, now at the Fort Worth Museum of Science and History, and another even more complete one from Oklahoma, nicknamed Fran, which is now at the North Carolina Museum of Natural Sciences. This specimen, the largest ever discovered, includes the only fully preserved skull and forelimbs of this species. In 2012, scientists confirmed the presence of Acrocanthosaurus in the Clovelly Formation in Wyoming after finding another partial skeleton from a younger individual. This fossil was found near the remains of a sauropod, showing that Acrocanthosaurus might have lived alongside other giant creatures. There are also other incomplete theropod remains from this region that might belong to Acrocanthosaurus, but some fossils found in the area have been misidentified. What makes Acrocanthosaurus particularly interesting is that, unlike many other large meat-eating dinosaurs, it lived in both the western and eastern parts of North America. While fossils from the western states were long known, the first clear evidence of its presence in the eastern US came in 2024, when a partial skeleton was discovered in the Arundel Formation of Maryland. This skeleton, identified as a young Acrocanthosaurus, is the first of its kind found in eastern North America and represents the smallest known individual of this species. Despite being mostly known from partial fossils, Acrocanthosaurus has been found in other areas outside its main range. A tooth discovered in southern Arizona has been linked to the species, and similar tooth marks were found on the bones of a sauropod in the same area. While there are other possible Acrocanthosaurus fossils scattered across different regions, many of these remain debated. Acrocanthosaurus was an impressive predator, estimated to reach lengths of 36 to 38 ft and weighing up to 7 tons. Its skull, which was over 4 ft long, gave it a fierce look, and its strong body would have made it one of the most terrifying creatures in its environment. The skull of Acrocanthosaurus, like many other relatives in the Allosauridae group, had a long, narrow and low shape. A large opening in front of the eye socket, known as the antorbital fenestra, helped reduce its weight. This opening was bigger than a quarter of the skull's length and about 2/3 of its height. The surface of the upper jawbone, maxilla, and the top of the snout, nasal bone, were much smoother compared to the rough textures found in dinosaurs like Giganotosaurus or Carcharodontosaurus. Along the sides of its snout, from the nostrils to the eyes, were long ridges that started at the nasal bones and stretched over the lacrimal bones, a trait shared by all allosauroids. Unlike Allosaurus, Acrocanthosaurus didn't have a large crest in front of its eyes, but instead Its lacrimal and postorbital bones came together to form a thick brow above the eye, resembling the structure seen in other large theropods like Carcharodontosaurus and Abelisaurids. The upper jaw had 19 curved, serrated teeth on each side, though no details have been published about the lower jaw's teeth. The teeth of Acrocanthosaurus were wider and lacked the wrinkles found in Carcharodontosaurus teeth. Its lower jaw, dentary, was squared off at the front, similar to Giganotosaurus, and became deeper toward the back. A prominent horizontal ridge on the outer surface of its jawbone, called the surangula, was thick and ran along the underside of the skull joint, similar to the Giganotosaurus. The most striking feature of Acrocanthosaurus was its row of tall spines along its neck, back, hips, and upper tail vertebrae. These spines were more than 2 1/2 times the height of the vertebrae from which they rose. While other dinosaurs like Spinosaurus from Africa had even taller spines, some reaching up to 6.6 ft, the spines of Acrocanthosaurus were still notable. The lower spines had attachments for strong muscles, similar to those of modern bison, which probably supported a thick ridge along its back. The exact purpose of these spines remains a mystery, but they may have been used for communication, fat storage, muscle attachment, or regulating temperature. The vertebrae of Acrocanthosaurus, including its neck and back, had deep depressions, called pleurocoels, while its tail vertebrae had smaller ones. This feature was more similar to other Carcharodontosaurids than to Allosaurus. Acrocanthosaurus had a typical allosauroid skeleton. It was a bipedal dinosaur, walking on 2 legs, with a long, heavy tail that helped balance its body and keep its center of gravity over its hips. Its arms were shorter and more robust than those of Allosaurus, though they still had 3 claws on each hand. Unlike smaller, faster dinosaurs, Acrocanthosaurus had a longer femur than tibia, indicating it wasn't built for speed. Its hind limbs were sturdier than those of Allosaurus, and its feet had 4 toes, with the first toe being much smaller and not touching the ground as in many theropods. Acrocanthosaurus is part of the Allosauroidea superfamily, which is known for its paired ridges on the nasal and lacrimal bones and tall neural spines on the neck vertebrae. It was originally placed in the Allosauridae family with Allosaurus, but later studies found it to be more closely related to the Carcharodontosauridae family. When it was first discovered, Acrocanthosaurus, along with many other large theropods, was only known from incomplete remains, which led to varying interpretations of its classification. Initially, paleontologists like J. Willis Stovall and Juan Langston Jr. placed it in a family called Antrodemidae, later transferring it to the Megalosauridae family, a catch-all category for many theropods. The long spines of Acrocanthosaurus also led some researchers to link it to Spinosaurus, a connection that persisted into the 1980s. In 1988, Gregory S. Paul named a species called A. altispinax, based on similar spines found in the early Cretaceous of England. But these were eventually reclassified under a different genus, Becklespinax. Most modern studies place Acrocanthosaurus within the Carcharodontosauridae family, often in a basal position relative to Carcharodontosaurus and Giganotosaurus. Some analyses suggest that Acrocanthosaurus is closely related to Eocarcharia, another African theropod. Fossils of Neovenator from England are sometimes considered even more primitive, or part of a closely related group called Neovenatoridae. This points to the possibility that the Carcharodontosauridae family originated in Europe and spread to other parts of the world, including North America. All known members of this group lived during the early to middle Cretaceous period.